Log on, tune in, find out. Another good idea from Cambridge.
And we will start with the first lecture, that is Norbert Hoffmann on augmented bundles.
Good morning. So let me start by thanking the organizers and the Newton Institute for the invitation to come here and for the opportunity to lecture to you. So I'll speak about augmented bundles. Today and tomorrow, augmented bundles. And the first thing is, of course, to tell you what that means. What are augmented bundles? So I will work over a smooth projective curve over the complex numbers all the time. So in other words, over a compact Riemann surface. Much of that can be done more generally, also on higher dimensional varieties or other fields, but to present the ideas, I would take the simplest and most curve, most classical case, which is this one. And maybe I have to start with a disappointment. I won't give a mathematical definition of what an augmented bundle is. I'm not sure there is agreement on a precise mathematical definition of what that is. It's more like an adjective which covers a lot of examples which have some common features that I'm trying to present here. So let me give some typical examples of what people mean by augmented bundles. I'll always denote the augmented bundles by letters like E, so it will be augmented bundles over X, and there are various kinds, some of which I will mention now as typical examples. So augmented bundles means, first of all, they are bundles and then they are augmented by something. So they are underlying bundles. These are algebraic or holomorphic, which is the same, vector bundles over X. And I will always denote the underlying vector bundle of an augmented bundle E by symbol like E check. So E check will always be an algebraic or equivalently holomorphic vector bundle over this compact Riemann surface X. And then there are various types of augmented bundles where this underlying vector bundle is augmented by some kind of extra structure. For example, so there are the quasi-parabolic bundles, which are a pair consisting of an underlying vector bundle and a vector subspace in one fiber of that vector bundle. So such a pair is called a quasi-parabolic bundle. So small x here is one closed point of the curve, one point of the compact Riemann surface, which is kept fixed all the time. So it's chosen once and for all. So this is the fiber of the vector bundle at that point, and a pair consisting of an underlying vector bundle and a vector subspace in one particular fiber is called a quasi-parabolic bundle. In fact, there are more general versions with flags or with several points, but let's stick to the simplest case. So this is one kind of augmented bundle, quasi-parabolic bundles. The next are next kind I'd like to mention are the coherent systems. So these are also pairs consisting of an underlying vector bundle and a vector subspace in the space of global sections, holomorphic global sections of this underlying bundle. So such a pair is called a coherent system. That's an underlying vector bundle augmented, so endowed with the extra structure of a vector subspace in its complex vector space of global sections. And there's one more kind. There are many more kinds, but one more which I would like to follow as an example throughout the lecture. These are the Higgs bundles. So these are pairs consisting of, again, an underlying vector bundle and then a morphism of vector bundles, theta, from this underlying vector bundle to its tensor product with the canonical line bundle of the curve of the compact Riemann surface. So such a pair consisting of a vector bundle and such a morphism is called a Higgs bundle. That's also an example of what people call an augmented bundle. So these are the three main examples that I will follow throughout the lectures. And so it's quite a challenge to say something about the history, because there are many different reasons and motivations why people looked at such extra structures, and many people who contributed to that. So I'll try to say a few names and apologize to everybody whom I forgot. Well, the quasi-parabolic bundles were invented by Mehta and Seshadri, and then there's work on them, for example, by Boden, Hu, and Thaddeus. The coherent systems, some names are Bradlow, Brambilla-Paz, Garcia-Prada, Leportier, Newstead, Techidor, many others. Higgs bundles were, I think, kind of invented or discovered by Hitchin, and then there's work by Nitsure, for example, and by Simpson, who generalized it to higher dimensions, and much more work. So there's a broad spectrum of reasons why people are interested in such extra structures, and many others. So these are only examples. Let me maybe mention a few further examples which I won't follow so systematically later on. Further examples are, for example, triples consisting of two underlying vector bundles and a map between them. A morphism of holomorphic vector bundles between them. So these are called holomorphic triples. And have been studied, for example, by Alvarez Consul, Bradlow, Garcia Prada, Goten, Schmidt, and others. And there's one more example which I'd like to mention. These are the so-called framed bundles. These are pairs consisting of an underlying vector bundle together with a map from that vector bundle to one fixed coherent sheaf on X. So these are called framed bundles. So here F is one fixed coherent sheaf on the compact Riemann surface X, and these have been studied, for example, by Heubrechts and Lehn. So vector bundles with such endowed with extra structure of this sort are called augmented bundles, and that's what my lectures today and tomorrow are about. So the first thing you can say about such a bundle is the first thing you can talk about is its kind of discrete numerical invariance. And they are usually gathered in something which is called the type of an augmented bundle. And this is, in the three main cases of my lectures, these are just the following integers. In the quasi-parabolic case, well, what you have a vector bundle and a vector subspace. So there are three obvious numerical invariants, namely the rank of the underlying vector bundle, its degree, so if you like the first Chern class, or the number of zeros minus poles counted with multiplicity of any meromorphic section, and the third numerical invariant is the dimension of the linear subspace that is part of the datum. Yeah? So this gives you a triple of integers. That's the type in this case. And there's a similar notion in the other cases. So for coherent system, you again have a vector bundle and a linear subspace, so you can just take the same three integers and again get a triple of integers. And for Higgs bundles, well, there's only the rank and the degree of the underlying vector bundle. So in this case, the type is a pair of integers. And in general, it will always be a vector of integers, which kind of gathers the discrete numerical invariance. Now, good part of the theory of vector bundles is just adapted and redone, taking these extra structures into account. And that is the story I'm about to tell. For example, quite an important notion is the notion of subbundle, which has a variant taking the extra structure, the augmentation, into account. This looks as follows. So one augmented bundle E prime. So let this be an augmented bundle. So it has an underlying vector bundle E prime check and then some extra structure, and we say that it is a subbundle in the augmented sense of another augmented bundle E if, well, first of all, the underlying vector bundle is a subbundle. And then there are conditions taking the augmentation into account, and they look as follows. For quasi-parabolic bundles, the condition is just that the vector space V prime, which is the augmentation of this vector bundle, is precisely the induced one. So from V. So there's V, which is the augmentation here. This is a linear subspace in the fiber of the big bundle, so we can intersect it with the fiber of the small bundle and get a subspace in the fiber of the small bundle. And if this pair E prime consists of a subbundle endowed with this linear subspace, then we say it is an augmented subbundle of E. So that's a notion of subbundle taking into account the augmentation and There are similar notions in the other examples. So let me mention what it looks like for coherent systems. Essentially the same story. So you take the vector space and intersect it. So this is a vector space of sections of the big bundle, and you can intersect it with global sections of the small underlying bundle. And so if the augmentation of E prime check is precisely this one, then E prime is an augmented subbundle, is a subcoherent system of E. And for Higgs bundles, the condition is just that the Higgs field, so this morphism is called the Higgs field of the bundle, this morphism theta. The condition is that this is the restriction. So the Higgs field of the smaller Higgs bundle is the restriction of the Higgs field of the bigger Higgs bundle. Now, I'd like to point out that this places a restriction on the underlying vector subbundle. Yeah? So in these two cases, you could take any vector subbundle, and it would get an induced augmented structure, which turns it into an augmented subbundle. This is not the case in the Higgs case. Here the condition is that, so this can only be true if the Higgs field preserves the subbundle. So theta E check prime, if E check prime is a vector subbundle of the underlying vector bundle here, and the Higgs field preserves it in this sense, then the restriction of theta will be a Higgs field on the subbundle. So in this case, not all vector subbundles give augmented subbundles, only some of them. So that is to convince you that there's an appropriate notion of subbundle in each case of augmented bundles. And just to give you a chance to do something by yourself and get a little bit used to these definitions. Here's a small first exercise. I've written down a notion of subbundle. In each case, there is a corresponding notion of quotient bundle. So the first part of the exercise is to make sense of that. So whenever you have an augmented bundle and a subbundle in this sense, you can construct the augmented quotient bundle. And to do that is the first part of the exercise. Augmented quotient bundle E modulo E prime. And then the second part is to convince yourself that this is compatible with the discrete invariance. So the type, whenever you have an augmented bundle and a subbundle, then the type of the big bundle is the sum of the types of the subbundle and the quotient bundle that you've just constructed in the first part of the exercise. So the moral somehow seems to be that usually it's possible to treat the whole tuple, the whole pair, the whole augmented bundle very much in the way that classically one treats the vector bundle alone. And there's more of that sort. There's also a notion of morphism of augmented bundles. So if we have two morphism, if we have two augmented bundles, E1 and E2, and the morphism of augmented bundles is a morphism of the underlying vector bundles. Such that well, generally speaking, it respects the augmented structure. And what does that mean in the three main cases that I'm talking about? The other cases, then you can probably guess. In the quasi-parabolic case, the condition is that the fiber of the morphism of underlying vector bundles, so its restriction to the point x, maps the subspace V1, which is part of the augmented structure on E1, into the subspace V2, which is part of the augmented structure of E2. So it respects this subspace, or more generally, if you have a flag, it respects the flag. That's the condition for quasi-parabolic bundles. For coherent systems, it again looks quite similar. In this case, this morphism of the underlying vector bundles gives you a linear map between global sections from here to here. And the condition is that this induced map of global sections, which I'll denote by phi check lower star, maps the vector space V1, which is the augmentation on E1, into, so the image of V1 is contained in the vector space V2, which is the augmentation on E2. So that's the natural requirement for preserving the extra structure. For Higgs, in the Higgs case, the condition is just to commute with the Higgs fields, with the two Higgs fields. Yeah. So in this case, let me write it down first. We can either map with a morphism from one underlying bundle to the other, and then map with the Higgs field of the second bundle. There are Higgs fields, here are Higgs fields, yeah, to E2 check tensor omega. Or we can first use the Higgs field of the first bundle and then the morphism of underlying bundles. And if this is the same, so this morphism intertwines the two Higgs fields in this sense, then we say this is a morphism of Higgs bundles. So a lot of definitions which might be easy to guess, but I'm trying to convey that there is in each case there is an appropriate notion, and that's what it looks like in these cases. So here's another small exercise to give you a chance to get used to that if you haven't seen it before. So I've now defined what augmented bundles are and what morphisms between them are. So this would most likely be a category, and in fact the exercise for you is to check that this in each case defines category, and not just a category, an additive category. In each case. So additive category means, first of all, that the space of maps between two objects is an abelian group, and that there are finite direct sums which then coincide with finite products. So even these pairs, just like vector bundles alone, such pairs consisting of vector bundles and such kind of augmentation are in a sense quite linear objects. And just like for vector bundles, if you want to prove something specific, often you end up having to compute or estimate or show vanishing of some kind of cohomology. And the same, this has a variant in the augmented world as well, which I'd like to mention now. So I'd like to introduce a little bit of homological algebra in the augmented setting. let me start by reminding you of, which you've probably all seen, of Čech cohomology. So we're just on a curve. So there are open affine coverings consisting of just two pieces. And I want to pick one. So choose an affine open covering of the curve. If you've made that choice, then you can associate to every coherent sheaf on the curve its Čech complex, which I'm going to denote by C bullet of F. So in this case, this is just a complex of length 1, if you like. So it consists of two complex vector spaces, and the first of which is just the direct sum of global sections of F over U prime and over U double prime, and the second one is just global sections of F over the intersection. Yeah, so this is the Čech complex in this very small and simple case. And it, of course, computes the cohomology, the Zariski cohomology of this sheaf. And it can also be used to compute something slightly more complicated, which I'd like to remind you now of. This is the hypercohomology. So there's something called hypercohomology. I'll just say a few words about it, but I'll first write down the symbol. It's blackboard boldface HN of. So hypercohomology is defined for not just a single sheaf on your space, in this case on the curve X, but for a complex of sheaves. And I'm just going to talk about complexes of length 1. So complexes consisting of two coherent sheaves on X and a map between them. But hypercohomology is defined for any complex, and it is defined very much in the way cohomology is defined. Yeah? So for cohomology, you resolve your one sheaf by a good resolution, for example, an injective resolution, and then apply global sections. And for hypercohomology, you do the same with the whole complex. So you find a quasi-isomorphic complex of injective sheaves, take global sections. So that's just a variant of the usual cohomology. But if that scares you, then I'm just going to use hypercohomology of such short complexes, and that can be written explicitly in terms of Čech cocycles. So if you like, you can take this as a definition. This is just the cohomology of something you might call the Čech resolution of this complex, which, since it has only length 1, is just a mapping cone. So it's just a mapping cone of the induced map between the two Čech complexes of these. So that's something very explicit. Čech complex of F0, Čech complex of F1, which are both just complexes of length 1. And then there's an induced map between them coming from the boundary operator in this short complex. And so if you form the mapping cone of this morphism of complexes, you get a complex of C vector spaces, and its cohomology is the hypercohomology of this one. Now, depending on which convention for the mapping cone you take, you might have to shift here or throw in some signs or so. I don't want to worry about that. Okay. And I've introduced that because there are not just morphisms, there are also extensions of augmented bundles. So if we have, if we are still given two augmented bundles, E1 and E2, there is something you might call the Ext group or the Ext vector space. It's a finite dimensional complex vector space between these two. And this is defined as follows. Well, in the quasi-parabolic case, this is just ordinary sheaf cohomology, Hn, of x with values in the following sheaf. It's the sheaf of quasi-parabolic morphisms, of augmented morphisms from E1 to E2. So it's a sheaf on X, and it assigns to every Zariski open part U of X the complex vector space of morphisms, augmented morphisms, from the restriction of E1 to the restriction of E2. So what does that mean? Well, these are quasi-parabolic bundles. So these are vector bundles endowed with a linear subspace in the fiber over the point X. So if X is this point X, if we have an open subset U which does not contain this point X, then here I just mean the morphisms of the underlying vector bundles. And if the point X is contained in U, then here I mean the quasi-parabolic morphisms, so the morphisms of the underlying vector bundles whose restriction to the point X respects the subspace. So this is the sheaf of quasi-parabolic morphisms from E1 to E2, and its sheaf cohomology is the quasi-parabolic X groups. So that's an important invariant if you want to prove specific things about the geometry of the moduli space. You most likely end up trying to compute dimensions of such or prove that they vanish or things like that. For coherent systems, the expression is a little more complicated, but there still is a very explicit one. It looks as follows. So this is again cohomology of some mapping cone. So I'll just write down a morphism of complexes of complex vector spaces now. The first complex is just the Čech complex of E1 Čech dual, so the underlying vector bundle of E1 dualized with the and tensored with the underlying vector bundle of E2. Yeah, so this is just the bundle of morphisms between the underlying vector bundles. Yeah, this vector bundle on X. So take its Čech complex. So if you would take H1 of that, you would just get Xn of the underlying vector bundles. But now the augmentation has to come into play somehow, and it comes into play by taking the mapping cone of a morphism of complexes from this into some other one, which looks as follows. It is V1 dual. So V1 is the augmentation of E1. Yeah? So E1 is a coherent system, so it's an underlying vector bundle together with a vector subspace V1 in its global sections. Now you tensor that over C with the Čech complex of the underlying vector bundle E2 Čech, but that is still augmented a bit. So you take V2. V2 is a vector space of global sections of E2 check. Yeah. So V2 maps to H0 of E2 check, in particular to 0 chains. So there's a natural map here. This is a complex with 2 terms. Take this as a 3rd term and this map. So here you have a complex of length 3. Tensor that over the complex numbers with V1 dual, which means just take a direct sum of some copies. So here is a complex of length 3. And this has a map. I take the mapping cone of that. So let me give names to the maps. This is, well, we have 2 coherent systems, which means we have inclusions I nu of vector spaces V nu into global sections of the underlying vector bundles E check nu. And so this map is just induced by the inclusion of V2 into global sections of the second bundle. And this map is just a pullback from E1 to this vector space of global sections of E1. So that is E1, I1 upper star. This is kind of restricting, restricting to these global sections V1, restricting from the whole bundle to these global sections. So anyway, there is a complex you can write down which computes these kind of X groups. And there's a similar thing for Higgs bundles. Actually, it's slightly more simple in the sense that it is not just a mapping cone, it is actual hypercohomology. Hn of x with values in the following complex of vector bundles. Well, the first thing is again just the bundle of morphisms of the underlying vector bundles E1 check and E2 check. So if you take hypercohomology of that, you just take cohomology of that and get X groups of the underlying vector bundles. But now the augmentation again comes into play. Check dual tensor E2 check tensor omega x. And the morphism between these two is well, there are 2 morphisms between these 2 bundles, namely the ones induced by the 2 Higgs fields. And what you take here is the difference of these. So theta 2 induces the Higgs field on the second bundle, induces a morphism from here to here. And pull back along theta 1 also does. Take the difference. This is a complex of length 1 of vector bundles on X, and its hypercohomology is the Higgs X group, if you like. So now that was maybe a quite complicated and scary, but
What do you mean that you're defining X?
sorry?
You already defined R.
Yes, that's part 1 of the following exercise. Check that X0 is home. So this exercise has the purpose that you play around a bit with this. This looks rather complicated, I admit, but it's quite explicit, and some things, if you just play around a little bit with it, will be easy to check. For example, thank you for the question. It's rather easy to check once you've played around with these definitions that X0 is canonically isomorphic to the Hom I've already defined. So this should in particular settle this slight ambiguity about the shifts. Yeah, so if you make it explicit, you should make the shifts here in such a way that in degree 0 you get home. And there's a second part, which let me put an asterisk there because that is a little more tedious, but still completely elementary. X1 E1 and E2 is the set of isomorphism classes of extensions of augmented extensions of E2 by E1. Yeah. So part of the exercise is to turn this into a more precise statement. But we already have a notion of subbundle and of quotient bundle. Where is it? Here, subbundle and quotient bundle. So from that it should be clear what a short exact sequence is. And then an extension is an isomorphism class of short exact sequences. And just like for vector bundles, with a little augmentation of the argument, you can check that this X1 classifies extensions, augmented extensions in this sense. And then now there's also X2. So things are a little more complicated here. The geometry will be more complicated than that of vector bundles on curves. But I mean, let me give you the exercise to describe X2 in terms of the underlying vector bundles and the augmentations. Still, there are many cases in which this vanishes. And then that is, I think, used often.
If it's not Unita X, why do we want this one?
Let me say, I guess it is Unita X. I'm not exactly sure, but I guess so. This one is more computable. I mean, how do you compute Unita? That is not so easy. Yeah. I mean, X1 is Unita. I'm still claiming this here, and I think X2.
I mean, are you saying
probably
that X2 is not 3-turn extensions? I mean, is it something else?
I'm not aware of this being checked somewhere, but I would expect it. I'm not sure. Yeah. I mean, first of all, these categories are not abelian, so some care is required there, but they have some weaker property. I think they are exact or quasi-abelian, something like that. I would be surprised if it's not Unita, but I don't know about it being checked. Okay, and just like for vector bundles, one important tool to compute dimensions of such X groups is Riemann-Roch. So there's an augmented Riemann-Roch. And with that definition, it is not difficult to prove. So that's the next exercise. Find a bilinear form in the types which computes the augmented Euler characteristic in that sense. So more precisely, if you plug in the type of two augmented bundles, so these couples of integers, E1 type E2, then what you get is the alternating sum of the dimensions of these X groups. Minus 1 to the n dimension of the complex numbers of xn. E1, E2. Yeah, so that's the, if you like, the augmented Riemann-Roch. And I think that's quite useful, for example, if you want to know things like the dimension of moduli spaces and so on. Okay. Can you read it if I write here? Yes? Okay, so maybe I do that. Switch off that. So in the last 15 minutes of today's lecture, I'd like to talk about families, because I want to get at moduli tomorrow. So maybe I don't write here. So I'll talk about families parametrized by some parameter scheme. And it's good enough, I think, to take parameter schemes of finite type. Over the complex numbers. Parameter scheme S. So what is a family of augmented bundles parametrized by S? I'll denote it by curly E, and it, of course, has an underlying vector bundle, which is curly E check and some extra structure. A family of augmented bundles over S. It consists of an underlying vector bundle, E check. So since it's going to be a family, that underlying vector bundle will now be over the product. And it is endowed with some family of augmentations. Let me just, to fix ideas, write down the definitions in these three cases again. So what is a family of augmentations for a quasi-parabolic bundle? Well, it should be at every point of S, it should be a vector subspace in the restriction to that point. So we take a subbundle. V is a subbundle in the restriction of the underlying vector bundle to that point x times S. So here we have now a vector bundle over S, and the augmentation consists of a subbundle, vector subbundle over S. So in the coherent system case, you do a similar thing, but there's some small print here. You take a locally free subsheaf in the push forward, in the push down. So you take the underlying vector bundle over x times S, push it down to S. That is kind of the relative version of its global sections. This is only a coherent sheaf on S in general. And you take a locally free subsheaf, locally free coherent subsheaf, but then I think you have to require a little more, namely that such that the induced map, so if you specialize now to a point, such that if you specialize to a closed point in the parameter space, then you only get a map, not necessarily an injection, between the fiber of this locally free sheaf and, well, first of all, the fiber of the push forward, but then by cohomology and base change, this again maps to, not isomorphically, but it maps to global sections of the restriction of E check and the condition is that this composition of the two maps is injective. Yeah. In the end, you want a coherent system at every point. So at least you should have a vector subspace here. So that is certainly necessary, and I think that's good enough to get a decent notion of family. And for Higgs bundles, it's again easier. The Higgs field should just be now a morphism of vector bundles over x times s. So it should map the underlying vector bundle E check to E check tensor. This is a vector bundle over x times s, and we tensor it over OX, so over one of the factors with the canonical bundle of the curve. Or if you like, you pull back the canonical bundle of the curve to the product. Yeah, so that's the notion of family. And here's another exercise. If you are given the underlying vector bundle, then you can parametrize quite neatly, quite easily, the augmented structures that there are on it. So let's look here. If you're given the underlying vector bundle E check, then quasi-parabolic structures are just parametrized by some Grassmannian, coherent systems also by some Grassmannian, and Higgs bundles on that underlying vector bundle just by some vector space of maps between these two. And that generalizes to families, although it gets a little bit more complicated here. That's why I make it an exercise. So given the underlying vector bundle E check and the type T, the exercise is to construct a scheme of finite type. So S is, in particular, S is given. Yeah, the parameter scheme is given. And the exercise is to construct a scheme of finite type over S tilde, which represents the following functor, representing the following functor. This is a functor from schemes of finite type over S to sets, and it sends every scheme of finite type T over S to the set of augmented structures on the pullback. So you are given the underlying vector bundle parametrized by S. You can pull it back to T. Now you have a vector bundle over X times T, and you can ask how many augmented structures has that.
Norbert, it's not visible from the back. Partly it's too low, and partly because of the projector in front of it. One problem you can solve. Just no, it's the whole box. Yeah, great. But it's the bottom line is still missing.
Thank you. Thank you very much. Okay.
Really just exercise 5, yeah.
Okay. Yeah, thank you very much. Of course, there's absolutely no point in me writing or saying anything that you can't read or hear. Five. So given the underlying vector bundle and the type, construct a scheme of finite type over the parameter scheme, which represents this functor. Finite schemes of finite type over S to sets, mapping each scheme over S to the set of augmented structures on the pullback family. Yeah. So as I said, if this is just a point, then here the representing scheme will just be this Grassmannian or this vector space of maps that I mentioned. This extends to families, although the dimension of the fibers may jump. So that is the main technical issue here. That the dimension may jump, but still you can represent it. You can put them into a scheme which might not be flat over S, which represents that.
Do you mean augmented structures of type T?
Yes, thank you. Yeah, otherwise it will not be finite type. It will just be a disjoint sum of infinitely many. So I've introduced the notion of family, of course, mainly to write down the moduli functor. Which I'm going to denote by curly m, x, and then depending on the type T, so this is a functor from the category of schemes of finite type over C, to sets, which sends each scheme to each scheme S of finite type over C, each such parameter scheme, to the set of all E over x times S of type T, and I mean here the set of all isomorphism classes. Yeah? So you take all families over x times S of type T at every point of S, and they're up to isomorphism. This gives you a set. This is the moduli functor. In fact, I'd also like to mention a variant. You can take a little more information and not just go to the set of all those, but go to the category, the groupoid of all those and the isomorphisms between them. You know? Groupoid of all those. So now it's a functor from a category to something of categories, so you have to make this more precise. I'm not going to do this now, but it can be done. And if you form that functor, that lax functor or 2 functor or what you like, that's what's called the moduli stack. So if you don't just take isomorphisms classes, but the groupoid of families and the isomorphisms between them. That time almost the same information, so I'm going to denote it by the same letter. And now in the last just a few more minutes, I'd like to say that we now already now we can compare this moduli problem to the moduli problem of the underlying vector bundles.
Well, why can you restrict only to schemes of finite type?
Oops. Maybe you'll see in a minute. I'll say in a minute that there are families of that there are families of finite type which capture all of them, kind of versal families. I'm going to write them down. If I forget, please ask again in a few minutes. Yeah? So the type starts with the rank and the degree in each case. So we have a morphism of moduli functors or moduli stacks, which just forgets the augmentation. and gets down to moduli of vector bundles. I'm going to denote them by m check because I always denoted the underlying vector bundle by m check. So this is now the moduli functor or moduli stack of the vector bundles, the underlying vector bundles E check over X. So there's this forgetful map, and if we write down the Hilbert polynomial of those vector bundles, so that's the Hilbert polynomial, which you can polynomial, which is some explicit polynomial in rank and degree by Riemann-Roch, but that doesn't matter so much. Then, well, there's a standard way to parametrize vector bundles. Vector bundles, if you twist them often enough with an ample line bundle, then they get Castelnuovo-Mumford regular, M regular, and then they are generated by their global sections, and you can write them as a quotient of their space of global sections. So that's a standard construction about moduli of vector bundles, which I'm recalling only very briefly. Which tells you that you get all vector bundles if you take the union over all integers m of vector bundles which are m regular, which means after m-fold twist they are generated by global sections and have no higher cohomology, and m regular ones are parametrized by some quad scheme. Yeah. So Qm is some, in fact, you have to take some open part of some quad scheme. Some quad scheme of quotients of rank R and degree D of, after twisting a trivial bundle, so you have to twist back. And the dimension of sections will just be given by the Hilbert polynomial. So that's the very much standard construction of moduli of vector bundles, which I won't recall in more details now here, because I would go heavily over time. And also the point of this lecture is, I think, to say what the augmentation does. So this parametrizes all bundles, and these are of finite type, these quad schemes. But now this parametrizes these bundles together with a choice of a basis of their global sections. And this can be removed by modding out by some group, GLP of M. So this is an open covering, in an appropriate sense, of the moduli functor or the moduli stack. That is, as I said, the standard construction for vector bundles. And the very last thing I would like to say today, this will fit in here, is that now that we can also parametrize on a given vector bundle all the augmented structures, that's what you have done here in this exercise, or what you are going to do, we can parametrize all augmented bundles. What we get is that the moduli functor or moduli stack is in a similar way a union over all integers of open pieces where the underlying vector bundle is M regular. And how do you parametrize those? Well, you just take the quad scheme and take the scheme of finite type over it, representing all augmented structures on the universal quotient. Yeah? So you can write in a similar fashion these moduli as such quotients. So parametrizing, very much like for vector bundles, parametrizing augmented bundles boils down to getting such a quotient. In particular, if you like the terminology of stack, which Kai Behrendt is also going to explain, then you see as a stack, this is an Artin stack. It has an open covering by quotients of schemes of finite types, modulo such smooth groups. And if you want a coarse moduli scheme, the problem is now to form such a quotient in the category of schemes. That I'm going to talk about tomorrow. And now coming back to your question, these are schemes of finite type over the complex number. And if I had written down here an appropriate definition with more general base schemes, then in any case, Zariski locally in the family, they would be pullbacks from kind of universal families on these quad schemes. So everything can be obtained by pullback from bases of finite type. Yeah? That's why it is enough to work with parameter schemes of finite type. Oh, I'm already a few minutes over time, and I've said what I wanted to say today, so thank you for your attention.
Are there any questions or comments?
So these quasi-parabolic bundles are kind of like, you take a vector bundle over a map from a point to a curve, and the coherent systems, they sound like take a vector bundle over the map from a curve to a point. Is there some general story of this form where I take vector bundle, a vector space object, and some category of sheaves over some diagram?
Yes,
make all this derivation all at once.
Yes, I mean there are several generalizations, more general notions, which cover some of those. Yeah, for example, what you mentioned, I think, so the dual notion to framed bundle would cover the two you mentioned, right? So there are more general notions. In fact, also much more general notions. Yeah. Sorry, that's I'm sorry. I think the most general notion is Alexander Schmidt's decorated vector bundles, which are also used to construct moduli of principal bundles. Yeah, I was trying to show the phenomena that the augmentation gives. That's why I picked the easiest. But there are certainly generalizations. Yeah.
Why is it one group? We see one group there, and for example, for decorated bundles, there's two groups, right? GLP. GLP1
yeah.
GLP2.
Okay, I've chosen somehow for simplicity. I've chosen the examples in such a way that they have only one underlying vector bundle. Right? If I had also included holomorphic triples, for example, I would have to take two groups in that case.
Any other questions? Thanks again.